Momentum and energy. And okay, so typically when you think of energy or firearms, shooting bullets and their velocity, you think of foot-pounds, so the amount of foot-pounds that a bullet has. Now, I have a video on foot-pounds. I think it's a ridiculous unit of energy, but at the end of the day, there's a bajillion different units of energy. It all measures the amount of energy an object has. So there's foot-pounds, there's British thermal units, there's BTUs, there's watt-hours, there's all sorts of random things. I can put a list here if I really feel like it. But anyway, it's kind of ridiculous. Energy, everybody's kind of familiar with it. It's the amount of energy something has in it. So we're familiar with in regards to batteries. We're familiar with in regard to like gasoline and diesel. We all buy energy and we use it for a thing. But what the heck is momentum, and why do we even care about that? So momentum is the tendency of an object that is moving to stay moving in that direction, or how hard it is to stop it moving in that direction. And so today we're going to go into a little bit of the physics of it, but we're going to tone it down, make it nice and simple. Okay, so for starters, let's start with the equations for energy. So we're just going to go energy here equals 1/2 mass times velocity squared. So this is kind of interesting, the velocity squared portion, because as I go to show you some examples, as your velocity goes up, it actually gets squared. So it's an exponential increase. So as if you had a plot of this is your velocity and this is your energy, as your velocity goes up, rather than it just going linear like that, it goes exponential. So velocity, if you increase your speed of your projectile, you exponentially increase your increase your energy. That's why you see some of these newer cartridges that they're doing really push the limits of the velocity and do like steel and brass bimetal cases, because it can really up your energy. Momentum, on the other hand, okay, it's not an M for momentum because that is mass. We just use that here. So momentum is a P. Why a P? I don't know, because physicists were drunk when they were making it. So momentum equals mass times velocity. It's a much simpler equation, but as you can see, your momentum, as your velocity increases, and if this is your momentum, it just increases linearly, where we saw the energy increase exponentially. Okay, so for starters, I'm going to show you what this equation looks like. So 1/2 mv squared, so we have a 100 grain projectile going 100 feet per second. So there's going to be 50 times 10,000 here. Okay, so then we get 500,000 grain foot squared per second. Okay, this unit is super janky. Nobody knows what the heck that is, but this is what you get when you multiply this. Guys, this is why the metric system makes so much more sense when doing physics and engineering calculations. I know y'all rag on it, but it is way nicer. So this, you got to convert this number. And in order to convert it to foot pounds, which I already have, oh gosh, foot pounds, I already have a whole video on what a foot-pound is. I'll put that here at the top. But you have to convert it by this nice handy number, 225,218.35. So 225, let's see, 218.35, and then this is going to get us our energy. So this gives us about 2.2 foot-pounds. Foot-pounds. Don't worry about that. Okay, so it's, as you can see, it's kind of a pain in the butt to do this math, but that's really what it is going to be. So I'm going to show you another example. Let's say we have the same 100 grain bullet. So our energy is equal to the 100 grain bullet. So 1/2 mass times our velocity. But let's go 3,000 feet per second. So this is really a cooking round, lightweight bullet, cooking round. And so we're going to get 50 times, this value is 450 million. And we divide that by the same constant here. I'm too lazy to write it. That's going to go there. And this is going to equal about 1,998 foot-pounds. And so you can see this is really start getting into 6.5 Creedmoor territory, maybe a little bit slower and a heavier projectile, and you're going to be, you know, about in the 2,500 range-ish. But so this is the calculation for how you do energy, and this is useful because let's say you're on a mountain, you're this dude here, you're on a mountain, and you got a little gun here, and you want to go hunting. So you want to go get this deer. This is a deer, by the way, if you couldn't tell, because I really studied in art class. And so you want a projectile. There's laws typically, or at least general guidelines for how much energy a projectile should have to take down different game like deer, elk, larger game, bears or whatever. And then this will let you know how much energy here that it's going to have. There's calculators online. Honestly, you can just search it and then it plugs it in. There's calculators that you can download so you can have it handy and calculate your energy. But essentially, that's how it's done. And so that is the difference between energy and momentum. Momentum is less useful for the context that we care about with firearms. Another difference between these two, and this really kind of gets in the nitty and gritty of physics, but momentum is a vector quantity, so it has a magnitude and a direction, whereas energy is just a scalar, so there's not a directional component with it. And energy can measure all sorts of things like thermal or potential energy or kinetic energy and all that. So, okay, so I hope that really kind of helped you understand a little bit the difference between momentum and energy. The TLDR is momentum is useful mostly in a physics context, but as far as this shooting firearms goes, we're mostly concerned with the energy component and calculating energy of projectiles. Anyway, if you have any other thoughts or comments on that, go look up a physics video, and please leave your comments in the comment section below. As always, guys, thanks for watching. See you on the next one.